Advanced Financial Modeling, Topic 6, Forwards and Futures, Learning Objective number 4. We're going to construct simulations using the normal, uniform, and triangular distributions. I think it's useful to step back now and talk about the process of running a Monte Carlo simulation. So you can think about it as in 3 steps to create a Monte Carlo simulation. One is you need to create a model with at least one input, for example, jet fuel prices, and one output, for example, unhedged cost. Second, you need to simulate random values for at least one input and specify a distribution, for example, a normal distribution, and record the output. Run the simulation and record the output. Once you've run, say, those 10,000 possible random variables for, say, appreciation of jet fuel, you then evaluate the results. And what that means is compute the mean, the standard deviation, the 90% confidence interval, the min, the max, and that you'll learn more about the model in question. So let's talk more about the choice of simulation or distributions. So far, the only thing we've used is a normal distribution. So you think about a normal distribution, it's bell-shaped curve, has a single peak, it's symmetric on both sides of that peak, and there's no min or max. In other words, there is always a chance you have a 10 or 15 standard deviation event. So those tails just kind of go out forever and just get thinner and thinner and thinner. But the question is, why a bell? Why couldn't it be a triangle? Why couldn't it be a rectangle? Why does it have to be a symmetric bell? Why can't it be an asymmetric bell? And those are logical questions. So we're going to talk about 2 other distributions that are commonly used in Monte Carlo simulations and finance, and corporate finance in particular. And that is a uniform distribution that instead of the normal bell-shaped curve in a uniform distribution, you just get a rectangle, and then the other one is a triangular distribution. So it's just different shapes. Now, when I say that's a different distribution, that means when we generate random numbers and you say graph those random appreciations or random prices or random quantities, when you use those other distributions, when you graph them, they will look like a rectangle, a triangle, or a bell-shaped curve. So let's think more about these 3 distributions: the normal, the uniform, and triangular. Normal is your bell-shaped curve. Uniform is a rectangular shape, and triangular is a it's a triangle shape. So it's just triangle, bell, and rectangle. In the normal distribution, there's a single peak. In a triangular distribution, there's a single peak. In a uniform distribution, there's no peak. You have a min, you have a max, and every number in the middle is equally likely. In a normal distribution, it's symmetric. In a uniform distribution, it's symmetric, meaning it's just a triangle. And in a triangular distribution, it could be symmetric or asymmetric. It could be symmetric like that, or it could be asymmetric like this. Both of those are triangles, but they could be asymmetric or symmetric. In a normal distribution, there's no min or max. You have random variables, they're less and less likely in the tails. In the uniform and in the triangular distribution, there's absolutely a min and a max at the points in which the rectangle or triangle touch that axis. What parameters do you need to estimate a normal distribution? You need a mean, that's the center point, and the standard deviation. For a uniform, all you need is a min and a max. Right? If you know a min, you know a max, you can define the distribution. For a triangular, you need three parameters. You need to know the min, the max, and the peak, the most likely value. All right, so why would we use different distributions? Well, you just think it'll fit the data better. It'll make more predictive of what future values could be. So for example, for appreciation of jet fuel prices, it's been shown that price appreciations or price changes tend to fall in normal distribution. So we'll tend to use normal distributions for price changes, or at least percent changes in price. However, you might talk to an analyst you're working on in corporate finance, and they may say, well, we expect to buy 150 gallons of fuel this year, but it could be as low as 90 and as high as 160, and we are really not sure which one it'll be. And it could be just as likely to be 90 or 160. Well, then you'd specify a rectangular or uniform distribution. However, you might be talking in marketing in another context, and they say sales will be between 100 and 200 with no likely value. Again, that's a rectangular distribution. However, in the second one, what if they say they're going to buy 150 gallons of fuel, but it could be, and that's the expected value. That's the expected value, and it could be as low as 90 or as high as 160. Well, then I would just use a triangular distribution. So anytime you have a central tendency or an expected value, I will use a triangular distribution. And if it's the high number is just as likely as the low number, I'll use rectangular. So let's go ahead and do some modeling on these three distributions. And specifically, we're going to talk about three possible jet fuel distributions. So I'll go to the spreadsheet, and we'll say that the jet fuel could be normally distributed with a mean of 150 and a standard deviation of 10. It could be uniformly distributed with a min of 90 and a max of 160, and it could be triangularly distributed with a mean of 150, a min of 90, and a max of 160. So how we could simulate that is we could write a formula for a simulated random value for the quantity. So what I'm going to do in this one is in the spreadsheet, I already have the rand function. Remember, rand gives you a random number between 0 and 1. Between 0 and 1 with a mean of 0.5. So if you want to simulate a normal distribution with a mean of 150 and a standard deviation of 10, I will just use the formula that is the mean plus norm S inverse rand. Rand is already given to you right there, times the standard deviation. So in this case, it's the 150 plus a random z, and that's a normally distributed z, times the standard deviation. So you see every time I hit F9, I get a new value for simulated gallons. If you want to use a uniform distribution, we use this formula. Min plus the random number, the 0, 1 random number, times the max of the min. So it's going to be the min plus that random number times the difference between the min and the max. So you can think of the difference between the min and max as the range. So let's think about what's happening here. This random number is between 0 and 1. We can look at that as I select or hit F9 a bunch of times. If that random number is 0, it gives you the min. If that random number is 1, it gives you what this function gives you is the max, because it's going to give you the min plus 1 times max minus min. So that's how this we'll call it formula works. It's always the min plus the random number between 0 and 1 times the range. And you can see those numbers are always between 90 and 160. Now the triangular distribution, it's a little bit tougher. And what I do is I've written a function for you in VBA called triang. And you have several parameters. You need a random number, a random value. That's that 0, 1 random number. You need the min, you need the max, and you need the most likely. That's the peak. And notice I've just done these at double precision floating, and double precision floating as the data type, just to kind of show how that works. They don't really have an effect on this one. The RV is a random number between 0 and 1, so that's that rand from the spreadsheet. And ML is the most likely value, or the peak. And what the function basically does is says if the random number is between some number, is it less than some number, then it's going to guess a random number on the left side of that peak. And if it's greater than that number, it's going to generate a random number on the right side of that peak. So we'll go ahead and use that function. I'll have that function for you on the exam if you need it. And so I'll pick up user defined and look for triang. I'll put in a random number, which is that rand up here, D9. I got a min, I got a max of 160, and a most likely is the peak. Hit OK. Now notice every time I hit F9, I get a random number between 90 and 160, except that they're going to be more values around the 150 value. Now I'm going to run a macro that's going to take whatever's in here, here, and here, these three random simulated gallons, and put them down here, 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 here. So we'll get 10,000 possible randoms for that. When I run that, I hit Alt F8. It's called distributions. That's the macro with that loop. I'll run that. Here's a counter over here, and you can see it's generating those 10,000 possible random variables based on those distributions. I'll pause for a minute and come back when it's done. Okay, I now have my 10,000 random variables for three of the distributions. If I were to graph the normal distribution and graph a histogram, which I did earlier, what you'd see is this data looks like this. Peak about 150, and it's got a bell-shaped curve. If I graph this data, it looks like this. It's all between 90 and 160, and there's no central tendency. And if I were to graph this data with a histogram, it looks like this, an asymmetric triangle, because I specified that the most likely is 150, the max is 160, and the min is 90. So this is a way of simulating random variables where you're not relying on normal distributions. And that becomes helpful because often in corporate finance or in business, you have an insight of what the most likely number is, and you have an insight of what the min and max is. You may not have an insight on what the standard deviation of my quantity is. So back to our problem with the Southwest hedging, or simulating Southwest possible costs. What if we leave the assumption that prices are normally distributed with a 20% standard deviation and at 6% expected return? However, what if we assume that the distribution for quantity is uniform between 90 and 160? Then all I need to do is change my formula for simulated quantity, and then I could run a simulation which uses that distribution. And so we'll go to the spreadsheet, go to Southwest Uniform, and all I need to do is update this one cell. Remember from the last slide, a uniform distribution is always going to be the min plus rand. That's a random number between 0 and 1 times the difference between max and min. So now there is my random quantity in there. Again, I'll look at that one more time. So you see a lot of numbers centered around 150. No number less than 90, no number greater than 160. Now I can run my simulation. It'll generate the unhedged cost, the hedged cost, and the quantity. I'm sorry, the quantity. So let's go ahead and run that simulation. It's called Southwest Uniform. That's the macro that has the loop. I'll run that. Be back as soon as that's done. Okay, simulation's done, and just by looking at it, it looks to be some kind of error. I want to do this just to show you this can happen. Remember, this is the hedge cost, so the quantities should be negative. And what that means is the unhedged costs are showing us as positive numbers. However, the hedge costs are larger, the risk is greater. That's because the hedge costs are not showing up as negatives. And when you put that together with the payoff of the forward, which are positive or negative depending on the price of the underlying asset and the payoff of the forward contract, it's actually doubling the risk in some sense. So that's because when you simulate purchases or acquisition of assets, you got to make sure that the quantity is negative. So if you ever run a simulated hedged profit or cost or revenue and the risk goes up, it's probably because of the sign of either the cost, the quantity, or the actual payoff of the forward contract, ST minus F or F minus ST. So always look for hedged cost or revenue to be lower distribution, 90% confidence interval than the other. So This is an easy fix. I'll go to my simulated costs. Simulated quantity. And I'm just going to put all of that in a bracket and put a negative sign in front of it. I'm going to rerun that. And what you should see is it will look a lot better. So I'm going to run that, Southwest Uniform Distribution. I'll pause it for a minute. And there it's completed. And what you see is the hedge cost, the range, or the 90% confidence interval, has gone from 206 to 476 to 249 to 421. And by the way, this model just had an 80% coverage ratio. So the idea, there's a lot of quantity uncertainty. So in this case, the person chose to only hedge 80% of the expected quantity, or 80% of 160 or 120. All right, so there we go. That's how you would use a uniform distribution, in this case, modeling the quantity. If you wanted to change this to triangular distribution, I would have to specify the peak, and I'd have to specify, or I have to use the triang function to use that. All right, so again, why do we use a coverage ratio of 120? Well, there's a lot of uncertainty here, the maximum being 160, so the person chose to hedge with a little bit less than the maximum, so they wound up using 80% of the maximum as the coverage ratio. Okay, so there we go. That is running a uniform distribution. I want to do a big warning at this point, and that is when you're simulating more than one variable for a particular model. In this case, we simulated prices and we simulated quantities purchased. The implicit assumption is that those two variables are independent, meaning think of it just mathematically, or in the spreadsheet, there's two RAND 0, 1s going on, and they're independent of each other. So if I were to calculate a correlation between the quantity and the price, there would be a zero correlation. They're uncorrelated. However, in some cases, you may have a model in which two variables are correlated. Say you have a model in which this company requires both diesel fuel and jet fuel. Now, those things are probably going to be relatively highly correlated to basic crude prices. So what you need to do is, in the model, you can't just generate the random numbers like we did. You have to generate something called correlated randoms. All right, that is not easy to do in Excel or VBA. It requires you to do something called a Cholesky decomposition that takes the first random number and generates the second random number. It transforms it in such a way that you get two correlated randoms. So all I'm saying is the tools you have so far don't allow you to model two random processes in one model that are correlated. The assumption is they're always uncorrelated, zero correlations. If you need to put that in there, you can either look at a Cholesky decomposition, you can Google that. However, software like Crystal Ball or At Risk by Palisades do that for you. It's just we didn't have the time to cover it in this course. It would take another week. So that's it. That's how you construct and simulate random numbers using normal, uniform, and triangular distributions.